So, welcome back. This is lecture number 55 and we will be discussing linear differential equations of first order, and we will go through the not only to the linear equations, but also the differential equations that are reducible to linear differential equations and also their solution techniques. So, just to recall from the previous lecture where we have discussed integrating factors. So, if our equation is given like m dx, m is a function of x y and n is also a function of x y. If this is a given differential equation which is not exact, and if we multiply that equation by this function I x y and then this equation becomes exact, then we call such a function here the integrating factor. And what we have also seen that how to evaluate integrating factor in some special cases. So, one of them was that if this m y minus n x over n is a function of x only, say f x, in that case the integrating factor we can evaluate simply by this e power integral f x dx. And also this case here 1 over m n x minus m y, if this is a function of y only, let us call it g y, in that case also we can compute this integrating factor again as I y is equal to e power the integral of this function g y dy. So, we require these knowledge of the integrating factor, how to evaluate in these special cases in today's lecture. So, here this linear differential equations, which is the topic of today's lecture. So, a first order differential equation is called linear if it can be written in this form dy over dx plus p x y and is equal to q. So, here this p is a function of x only and the q is also a function of x, but that can be a nonlinear function of x. Why we call this linear? This is basically linear equation in y, because this dy over dx appears as a single term, here also y is appearing just alone. So, there is no product of y with y or with its derivative. So, this equation is linear in y. The function p and the q may have powers of x. So, x square or any other function. So, no restriction on p and q, but this y has to be like dy over dx and here is y. So, that is a general form of first order linear equation which we will be considering in today's lecture, and this we can also rewritten as. So, this differential term here dx, we can multiply the whole equation by this differential term. So, we will get this differential of y plus p into y and this dx here, the right hand side also we will have qx dx. And now, this is the equation which is in this form, that m function of x y dx plus n function of x y and dy is equal to 0. So, here this is m with this dx and n x y is just 1 here, and then the right hand side instead of this 0 we have some function of qx dx. So, the important point is here this m dx plus n dy. The question is if we can find an integrating factor here for this, so that if we multiply by that integrating factor, so we get the total differential at the left hand side of this equation. So, let us look at it here. So, m is p y and this n is 1, the coefficient of this dy, and if we compute, if this 1 over n and dm del y, so del m del y minus del n del x, this term. So, what we are getting is just the function p which is a function of x alone. So, what is the point here? We can use this now, the idea which was explained on earlier slide. When this is a function of x only, then we have the integrating factor for this m dx and dy term. So, what is the integrating factor? The integrating factor will be this just the exponential of this integral p dx. So, we have this differential equation, we have the integrating factor here e power p dx, meaning that if we multiply by this integrating factor this given equation, that means e power square root p dx is appearing now here also in this term and the right hand side. Now, this part here, the left hand side, should be now the differential of some function f x y, that is the point. So, after multiplication here, this will become the total differential of some function of x y. So, here it is clear now that this term left hand side is nothing but the differential of this e power exponential p dx y. Why this is the differential here? So, if we just compute this e power p dx and y, so the differential definition is that the partial derivative with respect to x of this given function and then dx plus again the partial derivative with respect to y of this given function and then dy. So, here we have to get this partial derivative with respect to x only. So, y will be just taken as a constant. So, the exponential of this e power integral p dx. So, the exponential differential will be also the derivative will be the exponential only and then the derivative of this integral p dx with respect to x, and that will be coming as p. And here with respect to y, when we integrate, so this will become 1 and this e power p dx will remain and then this dy term, and here we have this dx term. So, this is the total differential of this e power integral p dx y. So, exactly that is what we have here, the p into y, the p into y, the exponential term with this dx and e power p dx with this y, e power p dx with this dy term. So, this is the total differential here of this function e power p dx into y, and then we have this right hand side as this q an exponential e power p dx and dx. So, what is the point now? That we can easily integrate this equation, because left hand side we have this differential of this e power p dx y and right hand side is some function of x. So, while integrating this, so we will get here when we integrate this e power p dx y only, and the right hand side when we integrate. So, we have q and this integrating factor dx, and we have this constant of integration. So, this is eventually the solution of this given differential equation, the given linear differential equation, and just to easy to remember, we write down as the y multiplied by this integrating factor, which we have to evaluate. And what is integrating factor? This integrating factor is nothing but this exponential p dx. So, with this integrating factor, what we write down, the y into this integrating factor is equal to the integral q, the right hand side of the linear equation, into this integrating factor, and we need to integrate here, and plus one constant of integration c. So, this is the formula which can be used to get the solution of the linear equation. So, this q is coming already in the right hand side, which was also in the equation, and the p comes here in the integrating factor, and then we can simply write down the solution of the differential equation. So, here just a note that sometimes the differential equation cannot be put in this form here, dy over dx plus pxy is equal to qx, meaning that it may not be possible to write down this equation as a linear equation in y. This is linear equation in y, the standard equation which we have considered before, but the equation can be put in the form here dx over dy plus p1 y x is equal to q1 y, meaning that instead of writing the equation which is linear in y, which may not be possible, but we have to also see this possibility whether the given equation may be written as a linear equation in x instead of y. And once we write down this equation, so now we will be just treating this x as we have treated y before, and because this is just the linear equation in x and we know the solution. So, we have to write down the integrating factor, where this p 1 y will come now here in the exponential there under the integral, and then the solution absolutely the same formula which we have used earlier, but now instead we have x into the integrating factor, and the right hand side this q 1 y again with the integrating factor, and this needs to be integrated over y and plus a constant c, constant of integration. So, that we have to also remember that the given differential equation may not be given as a linear equation in y, but if we take a close look, maybe we can write down this as a linear equation in x, and then we can use again the same idea having the integrating factor and then writing the solution. So, going through the example here, example number 1, we consider that 1 plus x square dy over dx plus 2 x y minus 4 x square is equal to 0. So, first we have to put into this form which we have discussed, that dy over dx. So, the standard form usually we considered as dy over dx plus this p, the function of x, into y, and is equal to this q x. So, we will put into this standard form, meaning we just need to divide this by 1 plus x square, and this minus 4 x square we can take to the right hand side. That means, the equation here by dividing this is dy over dx plus this 2 x divided by 1 plus x square with y, and the right hand side 4 x square over 1 plus x square. So, this equation is indeed in the linear form, linear in y, because we have y term here and also y term there. This is function of x alone. So, this is like p x in the standard form, the right hand side corresponds to the q x. Now, since this equation is linear in y, we can write down its integrating factor. So, the integrating factor will be the exponential of the integral and this p dx. So, p is 2 x over 1 plus x square. And now, what is this here? The differentiation of this 1 plus x square term is sitting there as 2 x. So, this is nothing but the logarithmic of 1 plus x square. So, here we have exponential of the ln 1 plus x square, which is equal to 1 plus x square, because the exponential will cancel out this logarithmic. So, we have this 1 plus x square as the integrating factor. So, having this integrating factor, now 1 plus x square, we can use directly the formula for writing down the solution, or we can multiply the given equation by this 1 plus x square, and then we can see the left hand side is a total differential of some function. So, the solution was y into the integrating factor equal to the right hand side, the q into integrating factor, and we need to integrate over this dx plus a constant c. So, here y into the integrating factor, that is 1 plus x square, is equal to the q is there 4 x square divided by 1 plus x square. So, this 1 plus x square will be cancelled out with the integrating factor. So, we will get 4 x square dx plus c. And now, here again 1 plus x square into y is equal to, this is 4 by 3 x cube and plus a constant term c, and that is the solution of the given differential equation. So, with the help of this integrating factor, we can compute the solution of a linear differential equation, as long as this p and q are some simple functions where we can integrate here and can find the integrating factor. The next example here, we have x plus 2 y cube and dy over dx is equal to y. So, what do we see here? Because y cube is appearing here. So, certainly the idea is that we cannot put into the form as linear in y, but we can try this equation to write down as a linear equation in x. And then, so we need to rewrite this as the dx over dy. So, that will go to the right hand side, we have dx over dy and minus this x term there, and then we need to divide also by y here. So, there will be 1 over y term x, and the right hand side will be 2 y square. So, what we have done now, so we have x plus 2 y cube, and then the right hand side is like dy into dx over dy. So, we divided by y. So, we get this x over y and plus 2 y square, and then this x over y we have taken to the left hand side. So, our equation is dx over dy minus this 1 over y into x and 2 y square. So, with this equation which is linear in x, because we have dx over dy term and x here in the right hand side. So, this corresponds to that p, and here corresponds to this q, which are functions of y alone when we have written this equation, linear equation in x. So, we need to compute the integrating factor again using the idea which we developed already. So, the exponential of integral and this term here minus 1 over y dy. So, which is minus of this ln y, the logarithmic y, or this minus can be taken here 1 over y, and then exponential and this logarithmic will cancel out, and we will get just 1 over y as the integrating factor. So, the integrating factor for this equation is 1 over y, and then we can use the formula that x into this integrating factor, which is 1 over y, is equal to the right hand side 2 y square, and then we have this integrating factor which is 1 over y and dy and plus this constant of integration. So, here this y will cancel out. So, we will get 2 y here dy, and then the integration will give us the y square. So, what we have here, the x over y is equal to x square plus c, and this is the solution of the given differential equation, the relation between this x and y. Next, what we will consider about these equations which are reducible to the linear forms. So, an equation of this form f prime y and dy over dx plus p and f y is equal to the q y. So, this equation is not linear in y because this f y is sitting here and also the f prime y is sitting here. The linear equation was dy over dx, p y is equal to q x. But what do we see here, that if the derivative of this term which is sitting with the p here, the f, and its derivative is just in front of this dy over dx. So, if we can pull our equation in this form, if we can write our equation in this form, then we will see now that this can be reduced to the linear form by appropriate substitution. And what is the substitution? We are going to have it here. So, if we substitute here f y, this function here is equal to v, some variable name we have introduced here, that this f y is equal to v. And then what we can get if we differentiate this, so f prime v, so the derivative of f with respect to y, so f prime y, and then dy over dx is equal to the right hand side will be dv over dx. And now we can substitute, and that was the point here, that this f prime dy over dx. So, f prime dy over dx is becoming now dv over dx. So, this term is dv over dx, then we have p and this f y is v and is equal to q x. So, the new equation which after this substitution, this equation reduces to dv over dx. So, this term with this derivative dv over dx plus the p into v. So, we have the p there and f y is substituted as v, and the right hand side equal to the q which is given there. So, what we observe now, this equation here, this equation is linear equation, linear differential equation, and that is linear in v. So, this is linear differential equation in the variable v, which we can solve for v, and then later on we can substitute this v as f y, and we can write down the solution in the form of y and x. As a special case here, we have the Bernoulli equation, and this is an equation this of the form the dy over dx plus py is equal to qy power n. This such a form of the equation is called Bernoulli equation, where this p and q are constants or functions of x. So, they can be functions of x, and this n is a constant except 0 and 1. So, it can take any other value other than this 0 and 1, and such equation is called Bernoulli's differential equation. So, this Bernoulli's differential equation is a special case of the idea we have discussed earlier, that it can be reduced to linear differential equation by an appropriate substitution. How we can do that here? So, if we divide this y power n, then this equation can be written as this 1 over y power n. So, this y power n goes to the left hand side in the denominator. So, 1 over y power n, then we have dy over dx, then p, and here y power n minus 1. So, this was y already. So, we got here y power n minus 1 and is equal to this q, the right hand side. And now, this is exactly the same which we have discussed earlier, that the function which is sitting with p, its derivative is somehow coming here as a factor of this dy over dx. That means, if we substitute this 1 over y power this n minus 1, 1 over y power n minus 1 as a function here as a variable v, and then what we see. So, if we differentiate here, what will happen? So, we have y power n minus n and plus 1. So, when we differentiate minus n power this n minus, so here we have n minus 1. So, again this was like y power minus n plus 1 is equal to v. So, when we differentiate this, what we will get? Minus n plus 1 and y power minus n plus 1 and minus 1, and dy over dx is equal to dv over dx. This is the differentiation here. So, this 1 minus n term is sitting here, and y power minus n is coming here, and dy over dx is equal to dv over dx. So, we have exactly the derivative of this written here, and now the idea was this y power minus n, which is here y power minus n with dy over dx. So, this term will become this dv over dx. This factor we can adjust by dividing this. So, once we substitute this 1 over y power n minus 1 is equal to v into this equation, what we will get? We will get 1 over 1 minus n and then just dv over dx. So, because we have to now we can think in this way. So, we multiply this equation, we multiply this whole equation by 1 minus n, and also so we can just 1 minus n. So, we have multiplied here 1 minus n, here also 1 minus n, and there also 1 minus n. So, this 1 minus n and y power this n minus 1 with dy over dx will become as dv over dx plus this 1 over. So, here 1 minus n will be there, and this p 1 over y n minus 1 will be v, and the right hand side the q with 1 minus n, and then we can divide again with this 1 minus n factor. So, we will get here 1 over 1 minus n dv over dx plus this p v is equal to this q, or we can write down in this form itself. So, because this is the standard form of the linear equation in v, because we have dv over dx term here and we have v here together with this 1 minus n, which is a constant, and this p could be a function of x, and then the right hand side this is function of x and multiplied by this 1 minus n. So, this is the linear equation in v. So, or this Bernoulli's equation we can convert by this such a substitution to the linear equation in this another variable v, and then we know how to solve a linear equation. Going through the examples. So, first example we will consider as x square minus 2 x plus 2 y square dx and 2 x y dy. So, this is written as m dx plus n dy form, but we can write down as dy over dx form. So, writing this into dy over dx form. So, we have 2 x y and dy over dx plus this x square minus 2 x plus this 2 y square, that is the term sitting here. So, we have divided just by this dx. So, we got this equation, and now we can take everything of this x to the right hand side. So, we have actually 2 y. So, we divide by x also. So, 2 y and this dy over dx plus this 2 y square over this x which we are dividing. The right hand side goes to now 2 x minus x square, and we have divided by x. So, we have rewritten this equation into this form, and now if we substitute here this y square as a new variable, then its differential derivative is sitting here next to this dy over dx. So, we can convert this to the linear equation. So, with this substitution y square is equal to v, we can get this 2 y and dy over dx as this dv over dx, and then we can substitute here. So, this term will become dv over dx, then we have 2 over x term together with this y square which is v, and the right hand side will be 2 minus x. So, this x when we divide we will get 2 minus x there. So, this is the linear equation in v, and we know how to solve a linear equation in v. So, we can write down the integrating factor, and this is our p here. So, e power this p dx which is x square now. So, 2 ln x or ln x square, exponential ln x square. So, here we get this x square. So, v into x square, the solution we can write down now. So, v multiplied by this x square, the right hand side here 2 minus x into this x square dx and plus a constant of integration here c. So, we get this v as y square, we substitute again. So, y square x square is equal to this 2 and this x square dx. So, 2 into x square dx means that when we integrate x cube by 3, this factor will come, and this minus this x cube which will become here x 4 divided by 4 and plus this a constant of integration. So, this is the solution of this given differential equation written in this x y as an implicit form. So, just one more example we will discuss here. So, dy over dx minus this y tan x is equal to minus y square sec x, for instance. So, if we divide by this y square, what we are getting 1 over y square dy over dx minus this 1 over y and this tan x, and then we have minus sec x there. So, it is a kind of Bernoulli's type of equation. So, if we substitute here this 1 over y as v, and then we differentiate here. So, we will get minus this 1 over y square dy over dx is equal to dv over dx. That is coming from this 1 over y is equal to v substitution. And then when we substitute back to this equation here 1 over y square dy over dx, that is dv over dx, and this 1 over y is v, this tan x and this minus sec x. So, minus also we have just multiplied. So, we got this equation dv over dx plus v tan x is equal to this sec x. And now, this is a linear equation in v which we can solve by calculating this integrating factor. So, the integrating factor will be exponential of this tan x. So, exponential this tan x, and tan x will be this after integral will become this ln sec x. So, the integrating factor is nothing but the sec x, which we can use now in the solution. So, the solution will be v into this sec x term is equal to the integral here this sec x, and then 1 this sec x will come. So, square dx and plus a constant of integration. So, we get this v into this sec x is equal to the integral of this sec square x, that is tan x plus this constant of integration, and this v was nothing but 1 over y. So, this 1 over y sec x is equal to tan x plus c, and that is the solution of the given differential equation written in this implicit form of the y and x. So, in fact, this we can write down as an explicit form also, because y appears here. So, we can bring everything to the another side of this y. So, the solution can be written in explicit form as well. So, coming to the conclusion, we have gone through the linear equations of order 1, and the standard form which we have discussed was dy over dx plus this p x y is equal to q x, and also we have discussed the equations which are reducible to linear differential equations of order 1 again, and there we have considered this again very general equation where this f y is sitting with p and its derivative, if we see it's lying here with this dy over dx, then by this substitution of this f y is equal to v, we can convert this equation into the equation into the linear equation which is in v, and then we can solve the linear differential equation which we have explained in today's lecture. So, these are the references used for preparing the lectures, and thank you for your attention.